Fantastic. So welcome back to the course of electrodynamics. And during the past lectures, we talked about how to find the potential in a general space, assuming that we know the charge distribution and we know the boundary condition. And we use the Green function, our Green theorem, to find the potential for two different scenarios, which one was based on the fact that the potential on the boundaries is known. So the problem was essentially finding you have different boundary conditions in different places, which you have either, I'm emphasizing this, either potential on the boundary or you do have derivative of potential, directional derivative of potential on the boundary. Okay. If you want, you can go also with x prime just to clarify that we are talking about that. Okay. And there were different boundary S1 until, I don't know, Sn. And we want to find out what is the potential at a given space here, which is phi of x. All right, and we had the coordinate here, and the coordinate indicates those places as a x prime, which you may have also in some regions. You may have also the charge distribution of rho of x prime. So in some places, or some places here, for example, you have a specific charge distribution. And we say that based on the fact that you know either the potential or the derivative, you can find an explicit expression in terms of summation, in terms of integral on the surface of the potential anywhere in that region. So, and that was given based on Dirichlet boundary condition, which we assume that for the case of Dirichlet, we know the potential on the surface. We know the potential on the surface. And we have Neumann boundary condition, which we know the derivative of the potential on the surface or on different surfaces that we have or on the boundaries. So, excuse me. So we clarify and we simplify the equations into let's say the problem into these two categories. And remember, you can have the potential and also the derivative of the potential for the entire the boundaries. This is what we call it. It's too much information, because when you know that potential, you can also take the derivative, or we know the derivative, you can also find the potential on the surface. However, it happens in some cases when you know potential for some of the boundaries and you know the derivative for some other boundary regions. In this case, we call it Cauchy boundary condition, and is a mixture of the two depending on the regions that you have. And you can solve the problem. And that is explicitly given by the expression that we do have here. Fantastic. So I don't have any problem with this. I mean, we can solve it directly for specific problems. We can find the potential based on that. We can discuss about the physics and what is the meaning of the physics that we do have, and many other situations. But before doing this, we have to clarify that the answer that we will get for Dirichlet or for Neumann boundary condition, they are unique. Okay? So assuming that, of course, we know that is the condition that we do have, which is this Laplacian. Okay. Of course, we have this property as well for the Green function, but we have to define that if we know that you are ending up with this problem, we have to know that if you are providing a specific boundary condition, then the answer is unique. Okay? You know what I mean? So I don't want to get a headache of finding a potential, and then I'm not sure that this potential is unique. Of course, with a constant, always constant can be neglected. Okay. Think about that and give me your thoughts. Okay. How to prove this?
So we already showed that if the curl and divergence of a field is like are like we know them, and also we know the value of the field on the boundaries. We know that that is unique, right? We proved that last session.
Yeah, so the previous lecture, we proved that if divergence of a vector is known, okay, which we call it source, and if we know that the curl of a vector also is known, which is a curl that you have, and we know A on the boundary, then A is uniquely defined, right? This is different. This was about the electric field and magnetic field. Now the question that I have, we started with this equation that Laplacian of phi of x is equal to minus 4 pi rho, minus rho divided by epsilon naught. All right, we had these, that was entire the problem that we started with. We say that we know the Laplacian, we know the Poisson equation, we know the Laplacian of the potential, which is given by the charge distribution divided by epsilon naught. And then we use the Green theorem, the second Green theorem, and we define what's going on based on the boundary condition, and then we got the solution. Okay. Now the question that I have, you have the regions that I just described, and for the entire the region, Laplacian of potential is given by minus rho divided by epsilon naught, right? And we know either the phi x on the surface, on the boundary, or we know the derivative of n at the boundary. Now prove to me that phi of x is uniquely defined. Because I don't want to waste my time on using the Green theorem, Neumann or Dirichlet boundary condition, Neumann or Green, Neumann or phi or Dirichlet Green functions, and solving the potential, and then I'm not sure about the uniqueness of the potential. Any thoughts?
So, can we use the previous method we used before? We make a contradiction, something like that.
Exactly. Let's go with that. The proof. Let's start. Let us assume that we have two different solutions to the Poisson equation. Okay, which is, I call them phi 1 of x and phi 2 of x. And we know that for these two, Laplacian of phi 1x is equal to minus rho divided by epsilon 0. And the same story for phi 2 of x, which is minus rho of x divided by epsilon naught. And at the boundary, we know that phi 1x is equal to phi 2x equal to a function f of x. This is at the boundary. And this is for the Dirichlet boundary condition. Okay? So what do you get from this relationship? We assume now that u is a new function which is defines the difference between x1, phi x1 and phi 1 of x and phi 2 of x. Then Laplacian of u is equal to 0. All right. And what is u at the boundary? Is 0. All right. Okay. Fantastic. So I end up with this equation that the Laplacian is equal to 0 and u at the boundary also is 0. Now let us use the first green theorem. What was the first green theorem? We used the divergence of psi gradient of phi, or if you would want to go with psi and phi, let's go with something else. Divergence of f gradient of g. So that we did the calculation, which was the gradient of f dot divergent of gradient of g plus f Laplacian of g. All right. Now we assume that f is equal to g is equal to u. Then from this we get divergence of u, gradient of u is equal to gradient of u square modulus plus u Laplacian of u. And we know that u Laplacian of u is equal to 0 from this relation that we do have. And now we can multiply this by the volume and bringing, writing the integral. So we have the divergence of u gradient of u d 3x is equal to integral of gradient of u power of 2 d3 of x, and that's on the volume. You can use the Gauss theorem and bringing the integral from the integral on the volume of divergence to the surface, and we end up with integral of u gradient of u dot n. Remember that d2 of x. That's on the surface, integral of v Laplacian, sorry, gradient of u power of 2 d3x. All right. So far so good, right? So, and we can write this, and we can just write that down. Is gradient of u power of 2 d3 of x on a volume is integral of equal to integral of u gradient of u dot n d2 on the surface. And for Dirichlet boundary condition that we discussed, what is the u value at the boundary?
0.
Is 0. So which means that for Dirichlet boundary condition, which is phi is defined at the boundary, then u is equal to 0 because it's a difference between phi 1 and phi 2. Then we end up with gradient of u absolute value power of 2 d3x is equal to 0. What you will get from this, and this is for any volume because we are solving this for any volume and any charge distribution. What does it mean?
The gradient of u has to equal 0.
Fantastic. So from here, we got the gradient, absolute value of gradient of u is equal to 0. What does it mean? That u can be a constant, right? Independent of the coordinate. But what is the u at the boundary? If it's a constant, it should be identical at the boundary as well, right? At the boundary, u is 0, so then u should be equal to 0. So we proved with this, let's say, relationship, we proved that u is equal to 0 if phi is defined at the boundary, and phi is following also the Poisson equation. Therefore, from here we get phi 1 is equal to phi 2. So the potential is uniquely defined in that region, in the volume. So knowing the Poisson equation, which means that you have a charge distribution, and knowing that the potential is defined at the boundary in all the boundary regions, then we are sure that we can find phi uniquely. So there's only one unique phi that solves this equation. What about the Neumann boundary condition? Do it at home, okay? It will be identical. The only difference is that for Neumann boundary condition, what you need to have the derivative of phi in the direction of n to be defined on the boundary, okay? And here we define u again as a phi 2 minus phi 1, which means that this term is defined and is equal to 0. And in the same fashion, you will get exactly the same result. Okay? The only difference is that you have a constant function, and again, you have to, the only difference is that, again, from the same relationship, you will get for Neumann, I will write it here, for Neumann boundary condition, you will get again gradient of u equal to 0. But what we know that directional derivative of u at the boundary is equal to 0. So what does it mean? That from these two relationships, you can solve this problem, and you will get u is equal to a constant, okay, because the derivative at the boundary is equal to 0. And again, from this relationship, what you will get that u is equal to a constant. It's not look like the other case, which is definitely 0. So the only difference is that in both Dirichlet and Neumann boundary condition, the potential is uniquely defined apart from a constant, okay, which we don't care. I mean, we know also from the physics perspective that electric field is important for us, and the electric field is given by minus gradient of phi in the electrostatic, okay, and therefore phi can be changed to any phi plus a constant function. And definitely minus gradient of phi plus a constant is equal to minus gradient of phi. So electric field is uniquely defined, force is uniquely defined, just the potential it can be changed. Look, there are phenomena explicit in quantum mechanics, like a Aharonov like the geometric phase, Aharonov-Bohm geometric phase, which in that case is the potential also they have a meaning, and they will give you a physical entity. So we will not discuss about that, but remember, in the context of electrodynamics, you have a gauge. Essentially, you can change the potential by a constant or by an explicit function, which we will discuss about that when we talk about electrodynamics. Okay, fantastic. So now we reach to the point that as soon as we know the Poisson equation and we know the boundary condition, which is phi or gradient of phi at the surface, then phi is uniquely defined in the region. Either you will use the Dirichlet or you will use the Neumann green functions. Okay, fantastic. Let's discuss about something else before going into solving the examples. Do you remember that I say that for the same region, we say that, okay, you have boundaries here, and we know that in this region, the gradient of a Laplacian of phi is equal to minus rho divided by epsilon 0. Okay, and the aim that we do have is, in order to find phi here, we need to know a green function. And green function defines based on the knowledge that you do have about the boundary condition. If phi is defined, then you will use the Dirichlet. If the derivative of phi is defined, you will use Neumann. Okay. So we know well. And what is the condition that you do have about the green function? Is the green function of x and x prime, if you take the Laplacian, is equal to minus 4 pi delta of x minus x prime. Do you agree about that? Can I change the green function, which is satisfying this relation, to another function? I will change now g of x and x prime to another function, which is g of x and x prime plus a function of x and x prime. So I change g to be equal to that one. But still, I know that the new g also gives me, the Laplacian will give me a minus 4 pi delta of x minus x prime. Okay. Still, for that one, also the Laplacian of g, I will write it as short, is equal to Laplacian of g and is equal to minus 4 pi delta of x minus x prime. What does it mean? That Laplacian of f of x and x prime is equal to 0. Do you agree with me on this? So I have a freedom in the choice of the green function. I can change the green function such a way with any other function of f, which we'll discuss what we mean by any. Okay, we have to be a little bit careful of that. With another function of f, and I will add it up to the green function, I will get a new green function because still that satisfies this, and I know that f of x and x prime also is equal to f of x prime and x. So it's symmetric with respect to x and x prime. So again, the same property, which is this one, and g of x and x prime equal to g of x prime and x is satisfied. So I have a new green function. However, I know that not all f functions, they will follow this relation, only those that they will give me x and x prime equal to 0. And it should be symmetric, okay? And else we will have a problem. What does it mean? So just to review, not to mess up with this situation, we have boundary conditions, and we are talking about finding finding potential, and we know that we need green function to define, and we know that the green function has a freedom of choice. What is this freedom of choice that we can choose? It's adding another function of f. But this function of f, the Laplacian of that should be equal to 0, and it should be symmetric with respect to x and x prime. So it means that essentially I can have this relationship, which is Laplacian of f is equal to 0 for this region. So indeed, the green function can be changed by adding another arbitrary function of f, which is following the Laplace equation, And this can be added to the term without having any problems and allows us to bring from one green function to another set of green function, to change from the Dirichlet boundary condition to Neumann boundary condition, depending on the problem that you do have. So this F has this freedom to allow you to move from one to another one. But F is following the Laplace equation. What does it mean, this following the Laplace equation? So Laplace equation, which is Laplacian of F equal to 0, talks about a region which has no charge. Okay? Do you agree with me, guys? So the Laplacian of F equal to 0, it means that there is no charge here. So then F function is taking care of any other charges or any other effects that happens outside of the volume. What is happening inside of these? What is happening inside of these? What is happening inside of these or inside of that? So this F function is responsible for those charge distributions there and allows you to move the boundary condition. Okay? So remember, in the choice of Dirichlet or Neumann, you have this freedom, and this freedom is how the charge distribution is moving or how the boundary conditions are set based on the charges that they are outside of the volume. Look, whatever we solve is for this region, which has a boundary with the free form shapes that I draw in a blue color. Okay, so we are talking about solving the Poisson equation here, but we are not absolutely touching anything inside of that, because this is the boundary that I do have. Okay, or this is the boundary that I do have. So F function is taking care of what is happening inside of these, which is outside the volume that I do have and I do care. Okay, and adjusting the boundaries for me. Good? Did you get the point? Any questions? Okay, fantastic. So recall and keep it in your memory. You can essentially use Dirichlet, Neumann, whatever you want. And you can find also the green function for the Dirichlet and using the F function to move it to Neumann. Okay? The choice is yours and the physics that is dictated here and the boundary situation. Now let's solve a couple of examples and clarify those points. I don't believe that I missed any important factors here, but let's solve an example for our case. How many minutes do we have? Yes, it's almost, yeah, we do have about 20 minutes. Let's solve a problem. So let's choose an example which is very realistic in some cases, assuming that, okay, I have, yes, this paper. I have this paper. Assuming this metal, okay, is a metallic paper, and this side is infinity. So I will not talk about what is happening below the surface. I'm talking about what is happening upper that surface. So I will assume that this is this object, which is the charger of my hearing aids, has a certain charge distribution, which I will give it, right? This has a specific charge distribution of rho of x prime. If I place this here, and the boundary is at the infinity, I can solve and find the potential everywhere. And what you need is just looking for 1 divided by 4 pi epsilon naught integral of the charge distribution divided by x minus x prime dx and d3x prime and solving it everywhere. Okay? This is what you need to do for this charge distribution when the boundary is at infinity. What is happening when I have a metal which is close to this and the metal is infinity? okay? And I kept this metal at 0. So what is happening when I keep this close to the Earth, which Earth has a 0 potential, essentially, and is conductive. And that's a problem that I will solve it. So I will bring this from infinity to here, and I will keep it at a certain distance of h, and then I want to find out the charge distribution. Definitely, this is a difficult problem at the first glance, right? Because this is a free form shape. So let's look at the problem. The problem is like this. I have a metal object, which means that is at 0 potential. What is the potential here? Is 0. Then I have an object which is having a charge distribution of x prime. And I will place it close. The center of this object is at the distance of, let's say, I don't know, z. And I want to find out what is the potential here. How should I solve this? So the problem is Laplacian of phi is equal to 0 in here, but in general, in this side is completely written as minus rho divided by epsilon naught. And I want to find this. I want to solve this and finding the phi there. And what is the boundary condition? That phi at this place, at the surface of the metal, is 0. And the goal is finding the potential here, not inside of the metal or other side of the metal. Any thoughts, guys?
Isn't it Dirichlet boundary condition since we have the phi on the edge?
Yes, the phi is 0. Definitely, you have to go with the Dirichlet boundary condition. So, what is the green function? Because I mean, essentially, I have to use Dirichlet. Let's write the Dirichlet boundary condition, and we will get 1 divided by 4 pi epsilon naught integral of rho of x prime, which I know what is the rho of x prime, GD of x and x prime was plus or minus, guys?
Minus.
Minus, yes. Minus 1 divided by 4 pi integral on the surface of phi of was phi at the surface or phi? X and derivative of GD of x and x prime d2 of x prime. Do you agree? Guys, do you agree on that? Fantastic. I know the potential on the surface is 0, right? At the boundary. So the second term is gone. So it's so simple, it's 1 divided by 4 pi epsilon naught integral of rho of x prime GD x and x prime. But the problem is that I don't know what is the GD of x and x prime for this specific problem. Or if I want to be careful, guys, for the, and I want to be more precise, for this specific geometry and boundary condition. So the goal is that as soon as you know the G, you can place it inside of that and you will solve the problem. It's so simple. Then the result is phi of x 1 divided by 4 pi epsilon naught integral of rho of x prime g of x and x prime, which is Dirichlet, d3 of x prime. For this specific problem, which the potential is equal to 0 at the boundary. That's it. How to find the green function. And what is this green function? What it should be look like? These are the problem that we know. That it should be minus 4 pi delta of x minus x prime. And g of d of x and x prime should be equal to g of x prime and x. Remember, gd of x and x prime is for these specific geometry and boundary condition. Which means that at the surface of the metal, at the boundary, G should be equal to
0.
Exactly, because that was the condition that we had it for the Dirichlet boundary condition. It should be the green function at the boundary should be equal to 0. And there's one boundary here, and that should be equal to 0. Now, that's a point. Go ahead and find the green function for this problem. We will find a way to solve this. And I mean, essentially, the entire this complicated problem is simplified into that Laplacian. And knowing that the green function should satisfy the boundary condition here, which is 0. How do you solve this? Any thoughts?
Have we used some trial solution?
Like what?
Like the one we had, 1 divided by x minus x prime plus some function.
Good point. Excellent. So that's a green function. We know that this is giving us minus 4 pi delta of x minus x prime. So Laplacian of f of x and x prime should be equal to 0. Now find f, guys.
Can we just put this term into our equation for the potential?
Yeah, we can place it there. Yeah, we can place it there, but it won't.
Nothing will come.
Nothing, because without knowing the f function,
Yeah, true.
we cannot solve that.
Sorry, where did we put the infinite surface? Is it like at x equal to 0?
That is, it's your choice. Is your choice, but I choose z. I have not yet defined the coordinate. It's up to you. You can define it as you wish. It can be x, it can be z, y, whatever. We are talking about the general problem in general. Any thoughts, guys? Tarek?
Before I say something, I just have a question. I know that this may have been discussed in the beginning of the class, but is the Laplacian with respect to f of x, like, is that defined with respect to x or with respect to x pi?
Look, this is what I have written here is Laplacian with respect to x inside of the green function that you place it here. Whatever you do, you get, you take the derivative with respect to prime.
Okay.
Okay, and then n prime that this. Okay.
Mhm.
Any thoughts?
Can we use one of our like Green's theory? Those
No,
no.
no. Sorry,
Can we,
Malika.
like replace x and x prime because they should have symmetry.
Let's solve it together, okay? It's more complicated than this. Let's do that. I will watch it from this perspective. So it means that that is my plane, which goes to infinity, okay? All right, and is grounded. So that is at zero potential. Or maybe I have to be careful with the notation. And I choose the coordinate x, y, let's say, yeah. This is x. This is y, which is orthogonal to that, and z is along this direction. Okay. And the charge distribution that I have is something like that. Can I assume that I can look at the in an infinitely small region there, which I have a charge of dq prime? Okay, let's assume that this charge, for simplicity, I will write it as a q, which is located at the distance of z at the height of x. And in that plane, it can be three-dimensional. You can expand it also in the along y direction, okay? Is y direction. But for simplicity, I'm just looking at the y equal to 0 plane. Do you agree, guys? That's a cross section that I will see. So I will extend it there. Let's review that if we talk about the charge distribution, also we are talking about individual charges. Can this charge distribution be a delta function? So it means that it's a point charge which is located here. That also should be true for this case. Do you agree? Okay. So I place a point charge here, and I have this boundary condition, and I have to solve the problem, and I have to be very careful that that should be the potential here at the surface, which means that potential at surface, which means that any x, any y, and z equal to 0 should be equal to 0. Do you agree? In that plane, that should be equal to 0. Doesn't matter where I am, but at z equal to 0 should be 0. Okay. And I want to find out what is going on with the potential everywhere. But remember, at this region, z greater than 0. I'm not talking about this region, z lower than 0. Okay? Because that's inside of the metal. I don't care at all. There's a boundary condition. That's the surface that split the two regions. Fantastic. So if the boundary condition, the metal was not there, the potential due to the point charge was given by 1 divided by 4 pi epsilon naught of q divided by x minus x prime. What is x prime? Is this location, is the location of this, which x prime essentially is x. Let's call these two x prime, okay, guys, just for having the same notation. X prime I hat plus z prime k hat. Do you agree? And we want to find the potential anywhere here, which is x. Not necessarily in the plane. It can be also out of the plane. Okay. So x, which is x I hat plus y j hat plus k n, sorry. Agreed? So I can write it down. So it will be 1 divided by 4 pi epsilon naught q divided by, that will be square root of x minus, sorry, my bad. X minus x prime power of 2 plus y power of 2 plus z minus z prime power of 2. This is the potential due to a single charge there, not assuming the boundary condition. Now that when we have a metal there, definitely the potential at the surface should be equal to 0. And the only way that I can make the potential to be 0 there is assuming that I have an identical charge which is located inside of the metal, okay, at the same distance. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So which is located here, and the same height. So that is located at minus z prime, but the same x prime. And this is a charge that is placed here. Okay. What is the charge value? Minus q. When I place a minus q here, what is happening with the potential between them? It will be 0. This is the way that it works. So now what is the potential due to this image charge, which is look like a mirror, which you are imaging the charge on the other side. So let's look at that. So essentially, I will get that's due to the real charge, that's due to the image charge, which is 1 divided by 4 pi epsilon naught minus q divided by x minus x second, which x second is this one. In general, x second always is a function of x prime. It depends on where the first charge is located. Okay, let's place it here. I will get 1 divided by 4 pi epsilon naught minus q divided by square root of x minus x prime power of 2 plus y power of 2 plus z plus z prime power of 2. Good? Yeah. Okay. Fantastic. The only difference is that z prime becomes minus z prime. Now, what I can say that the potential at x, but remember that here z is greater than 0, because I'm not allowed to talk about inside of metal. This is forbidden based on the discussion that we had, is given by 1 divided by 4 pi epsilon naught. Q can be factored out. Then I have the potential due to the real charge, which is 1 divided by x minus x prime power of 2 plus y power of 2 plus z minus z prime power of 2 minus the other term, which is, and that's power of 1/2, by the way, x minus x prime power of 2 plus y power of 2 plus z plus z prime power of 2. The entire of this is power of 1/2. Okay. Oh, let's write it more professional. Just write it in this way. And that is for z greater than 0. All right. Do you remember in the second lecture I gave you a problem, and I said to you that the green function essentially is the potential associated to the charge, which has the charge of 4 pi epsilon naught. And I say to you that's the potential due to that charge. Here, as soon as you find the potential, which for sure, what is potential at x, y, and z equal to 0? By the way, before going there, we want to verify what is going on with the potential at the boundary. That will be q divided by 4 pi epsilon naught, 1 divided by x minus x prime power of 2 plus y power of 2 plus z power of 2 power of 1/2 minus 1 divided by x minus x prime power of 2 plus y power of 2 plus z power of 2. Sorry, z prime power of 2 power of 1/2, and that is equal to 0. So that potential satisfies the boundary condition, which is equal to 0. All right. Now I will choose q equal to the 4 pi epsilon naught, and then I will tell you that the g of x and x prime, which I am looking for, due to that charge that I have it, is given by 1 divided by x minus x prime power of 2 plus y power of 2 plus z minus z prime power of 2 power of 1/2 minus 1 divided by x minus x prime power of 2 plus y power of 2 plus z minus plus z prime power of 2 power of 1/2. Okay. What is the g value at the boundary?
0.
Exactly, we just checked out. So that's a Dirichlet boundary condition, or the green function for Dirichlet. If I want to write it in the formalism, that is 1 divided by x minus x prime minus 1 divided by x minus x second, which x second was a function of x prime. All right, so this is exactly what Melika told us, that is 1 divided by x minus x prime plus f of x and x prime. And that is the f function that we were looking for. Clear? What time is it? 45. Then we will come back to this problem in a second. As soon as we know the g, which is the green function for Dirichlet boundary condition, which is that explicit boundary condition, then we can replace it inside and find the charge distribution. What is the charge distribution then? Sorry, the potential. Then we will find it as 1 divided by 4 pi epsilon naught integral of rho of x prime g d of x and x prime d3 of x prime minus 1 divided by 4 pi integral on the surface up of potential of x prime derivative n prime of g of x and x prime d3 x prime. So we know that this is 0 because the potential at the boundary is 0. Then easily what we will get is equal to 1 divided by 4 pi epsilon naught integral of any charge distribution, not only due to the charger of my hearing aids, but anything, it can be 2 pencils or I don't know, a mug at the front of an infinitely large metal surface, and the green function is essentially given by that term, which is 1 divided by square root of x minus x prime power of 2 plus y power of 2 plus z minus z prime power of 2 minus 1 divided by square root of x minus x prime power of 2 plus y power of 2 plus z prime power of 2 dx prime dy prime dz prime. Okay, good. And that's on volume that you do have. And the volume that we know is only on the volume that the charge, the volume of my mug or the volume of my the pencil or whatever that you do have. So as soon as you know the green function, then you solve it. You solve the problem. All right. So we will stop here. I think it's a proper time to stop, right? It's almost 4. So let's see each other at 4:05. I will pause the video and we will see each other at 4:05. Welcome back. Now we will follow the discussion. So the problem that we had so far was keeping the conductive at the 0 potential, then putting a charge, a charge distribution at the front of this. And then we finally got the green function, which, remember, this green function was for Dirichlet. So the green function was 0 at the boundary. Okay. And we got this explicit expression here. Note that for our problem, potential at the boundary was 0. That was the reason that we neglected this term. Okay. In general, even if this is the Dirichlet boundary condition, which the G at the boundary is 0, but potential can be a constant or can be a specific function there. So in general, this is not 0. For our problem is 0, but we looked into it. So so far, for the above problem, I don't want to go back. We found the potential, which is given by the potential is given by x1 divided by 4 pi epsilon naught integral of rho of x prime 1 divided by this. I'm writing it down because I need it for a specific reason. y2 plus z minus z prime power of 2 power of 1/2 minus 1 divided by x minus x prime power of 2 plus y power of 2 plus z prime power of 2 power of 1/2. Dx prime, dy prime, dz prime. All right. So now the problem was, what we solved, that was ground is a 0 potential at the boundary. And that was a specific charge distribution that we had. X, y, and z. Any charge distribution that you place it here will show up in the equation. What do you want me to solve, guys? Which problem? Which kind of charge distribution we should solve it? Any thoughts? Gavin is moving, so I think very likely he has a very difficult puzzle for me.
No, no,
I'll challenge the lecturer.
I was gonna say like a uniform sphere, you know, like I don't know.
Oh yeah, okay. Since you, I mean, in the break, Gavin, you asked about the physics. I will go back to the simple problem, and then I will extend it to a more complicated one. Okay. Tarek, you open the microphone. Do you want to say something? Just go ahead. Go ahead.
Was a question concerning like what we think is the charge distribution?
Yeah.
Okay. I was going to suggest something to the effect of a sum of delta functions, but
Okay. We can. That's the homework.
okay.
So let's go back to the previous question. Okay. Which, for this specific problem, I just want to verify because I want to discuss about some physics there. Assume that the charge distribution is a point charge distribution. We are very sure that the result is the same because we obtained just that based on the fact that we assume that a point charge. So assuming that the point charge is located, for simplicity, guys, look, I am doing that only for simplicity, at z equal to z prime. Okay, that's a z prime, it's a location. X is 0, y also is 0. Okay, so x prime is 0, y prime is 0, z prime exists. Okay, then how do you define a point charge, the charge distribution for a point charge? You write it rho of x prime is given by q delta of x prime, right? Everywhere the charge is 0 except at the point of x prime, which at the point of x prime is infinity essentially, but if you integrate it on a volume, then that will be equal to q. So integral of rho of x prime d3 of x prime will be equal to q. Okay, so we know that that's the value that we have. All right, so then phi of x, which means that potential anywhere here is given by 1 divided by 4 pi epsilon naught integral of q delta of x prime. Okay. Maybe the notation is not so convenient. Yeah, let's call it in this way. Z prime. I'm trying to find a way to simplify this. Let's call it, it's a little bit difficult because that's a fixed notation, fixed place. So I'll call it x00. So the place that the charge is located is, I call it 0 because I'm using the prime for the integrals. And that will be given by x prime minus x0, which is x0 is a location of the charge that I'm dealing with. Okay, is that fine, guys? Is it clear? Because I have a prime for the integral, and I am not allowed to use the prime anymore for the point charge. Then I will get that one as q delta of x prime. That's the scalar, is the x component, delta of y prime, delta of z minus z prime, which is z0. then dx prime, dy prime, dz prime, multiplied by the what we found as a green function for Dirichlet boundary condition that we have, which is 1 divided by x minus x prime power of 2 plus y power of 2 plus z minus z prime power of 2 power of 1. Okay, minus 1 divided by x minus x prime power of 2 plus y power of 2 plus z minus plus z prime power of 2 power of 1/2. Okay. This is multiplied, so this is multiplied by the lower. Okay. Good. And integral on x prime of delta will be 1. Integral of y prime delta will be 1. Integral of on the z prime, when you do it, any z prime will be replaced by z0. Okay. And that will be 1 divided by a q divided by 4 pi epsilon naught. Then that will be 1 divided by x power of 2 plus y power of 2 plus z minus z0 power of 2 power of 1/2 minus 1 divided by x squared plus y squared plus z plus z0 power of 2 power of 1/2. Clear? Good. So that is the potential that we found for this specific problem. Now let's look at the field. How do you find the field, guys? We found the potential because we want to find the field. Electric field is given by minus gradient of phi of x, which means that is given by minus ex. Oh, let's go. Is Cartesian coordinate that we choose is x hat derivative with respect to x, y hat derivative with respect to y, plus z hat derivative with respect to z of the phi of x, which we just had it here. Let's take the derivative with respect to x. Derivative with respect to x and y, they will be identical. Derivative with respect to z will be different, which we will do the calculation. So let's do the derivative with respect to x of the above potential, which will be phi of x. I will write it as a q divided by 4 pi epsilon naught. We have two terms that will be minus 1/2. Then it will be times 2. Then times 2x. Let's write it down. Derivative of that will be 2x. Then that will be 1 divided by x minus x prime power of 2 plus y. Oops, sorry. X power of 2 plus y power of 2 plus z minus z0 power of 2 power of 3 divided by 2. Agreed? I'm taking the derivative. And the second term will be minus by itself, which is, and then I have minus 1/2 again, multiplied by 2x. Then that will be 1 divided by x squared plus y squared plus z plus z0 power of 2 plus 3 2. A little bit simplifying this equation, the 2 goes away. Then I have minus q divided by 4 pi epsilon naught. X also can be factored out. Well, let's not factor it out for the time being. That will be x divided by x power of 2 plus y power of 2 plus z minus z0 power of 2 power of 3 divided by 2 minus x squared plus y squared plus z plus z0 power of 2 power of 3 divided by 2. That's the derivative with respect to x. Derivative with respect to y will be the same, just the only difference will be x is replaced by y because they are the same, the functionality. Derivative with respect to, I'm writing derivative with respect to also y, so of phi of x which will be minus q divided by 4 pi, oops, epsilon naught of y divided by x squared plus y squared plus z minus z0 power 2 divided by 3 minus y divided by x squared plus y squared plus z plus z0 power of 2 power of 3 half. Good. And what about derivative with respect to z of phi of x? Derivative with respect to x of this term, we are talking about this term, right? Because that's the potential, we just found it. It will be q divided by 4 pi epsilon naught. Derivative with respect to z, that will be minus 1/2. Then derivative with respect to argument of 2, z minus z0 power of 2, that will be 2 z minus z0. Okay, and then 1, again, the same scenario, 1 divided by x squared plus y squared plus z minus z0 power of 2 power of 3 half minus 1/2 of 2 z minus z0 plus z0, my apologies. And then that will be 1 divided by the same argument that we had in 3 power of 2. So let's simplify that. That will be minus q divided by 4 pi epsilon naught. Then that will be z minus z0 divided by x squared plus y squared plus z minus z0 power of 2 power of 3 divided by 2 minus z plus z0 x power of 2 plus y power of 2 plus z plus z0 power of 2 power of 3 divided by 2. Okay. Good. Fantastic. And now I have to multiply the first one by x hat, second one by y hat, last one by z hat, and summing all of them together. So I know that the first term for all of the three, they have the same denominator. I will take it out. So it will be e equal to minus, which goes away with the minus sign here. It will be q divided by 4 pi epsilon naught. Then it will be x hat, y hat, plus z minus z0, z hat, divided by x squared plus y squared plus z minus z0, power of 2, power of 3 divided by 2, minus the other term, which will be x hat plus y hat plus z minus z0, plus z0, z hat, divided by x squared plus y squared plus z plus z0, power of 2, power of 3 divided by 2. Good. I find the electric field. Yes. That's a simple dipole electric field, right? This is that dipole electric field that people, they get it in the second course of the second course of physics. In even maybe in, I remember in my not writing it in terms of vector notation, even in the time when I was in high school, we obtained this. Anyway, so good. So we finally used the green function for something useful. Fantastic. Huh, that's interesting. So that's essentially the electric field, which is a function, which is in the place of x. And remember, where is the location that electric field fulfill? Only at z greater than 0. That's it. We cannot apply that to the region which is inside of the material. All right. Oh, I have electric field. So essentially, if I place the charge here, this is at the potential of 0. I place the charge at the Z0 here. Then I will get electric field. Okay, I will get electric field here. So it means that there is a specific orientation for the electric field. Okay, or opposite direction, depends on the being positive or negative charge. I don't want to go for explicit one. So there will be a vector in Z greater than 0, which if I place a point charge here, infinitely small point charge here, it sees a force and moves around. Okay, I don't want to talk about the third charge, or let's say the second charge that applies there. But what is important, that what is electric field inside of the metal?
Should be 0.
Is 0. What is the electric field here? It is what we obtained from this relation. All right. Now I am asking, what is happening at the surface? All right. So if I have electric field here and I don't have electric field inside, so due to the continuity of electric field, do you remember that we should have a charge distribution at the surface? So what was the relation? E2n minus E1n is equal to sigma divided by epsilon 0. And remember that n is in the direction from 1 to 2. So if that region is a region 1, if that region is a region 2, that is the vector which is orthogonal to the surface, which is along go ahead.
Z, whatever.
Exactly, is along Z axis. It's a Z hat. So n hat is equal to Z hat. So now I know clearly, that was your question, Gavin, that what is happening physically there. So it seems that there will be a charge distribution at the surface of this infinitely large metal. So, and that charge distribution is given by here, by this equation. So let's write it down. E2n minus E1n is equal to sigma divided by epsilon naught. And for our geometry, E2 or EX Z, because only the Z component is important for us, or E dot Z, which is, again is EZ, will give us sigma divided by epsilon 0. What is the sigma? Charge distribution at the boundary, at the surface of the metallic plate. All right. So then I will write it down that E sigma is equal to epsilon naught, only the Z component. The Z component means what? This one with the negative sign. All right. So it will be Q divided by 4 pi epsilon naught, or here, guys, only the Z components will play a role of, okay, Z minus Z0 divided by x squared plus y squared plus Z minus Z0 power of 2, power of 3 divided by 2, minus Z minus Z plus Z0 divided by x squared plus y squared plus Z minus Z0. Sorry, plus Z0 power of 3 divided by 2. Good. Haha. I find that there is a charge distribution here, which is a function of x, y, and z. And of course, Z0, where is the location of that charge? If the charge is far away from the metal or close to the metal, then the charge distribution also will be affected. All right. Kevin, is that physics, right? That's exactly what we are looking for. So if you have a charge of Q, it seems that this charge of Q close to a surface of, let's say, if you keep it at the front of a metallic surface, which is infinitely large, but grounded at the potential of 0, it keeps the charge to the specific orientation here, or oriented the charge in a specific way, which you will see a specific charge distribution at the surface. Okay? And if you look at that relation, what is happening if you go far away in the transverse plane? So x squared plus y squared means that is a radial, because the charge and the surface, you can have an axis, right, oriented in the specific in that direction. Then around that you have a symmetric situation. So it doesn't matter what is happening with x, the same situation happens for y. Okay, this is the symmetry that you have in the system. There is no difference between x and y. You can just rotate it. So it means that it's a cylindrical coordinate. So you can transfer it to the cylindrical coordinate. Then you deal with x squared plus y squared as a rho square, and you have a z square as well, a z as a other parameter there. And it's rotationally invariant, so it's only function of rho. And then you will see that the charge distribution, if you go far away from x, so x is increasing or y is increasing or both, then what is happening, the charge distribution is decreasing because it's in denominator. Okay, larger x and y means lower sigma. So going far away from that axis, you will have less charge distribution. And close to that axis, you will have higher charge distribution. What is the total number of charge distribution, guys? We have to integrate it over entire the surface. So integral of sigma x, y, and z on the surface. Remember, that's on the surface, which means that dx, dy from minus infinity to plus infinity. Do that as an exercise, okay? And my recommendation is that transferring this into cylindrical coordinates. So it means that x squared plus y squared will be equal to rho squared, and dx dy will be equal to rho d theta. Integral on the theta is because it is invariant, so it will be 2 pi, and that can be simplified just by change of variable. What is your guess? What is the total charge distribution on the surface?
Q?
So close.
Isn't it
Nazanin?
minus q? Like they have.
Exactly. All right. So it tells us that that we use that image charge there, but in reality, what is happening? The charge distribution changes, but the total number of charges is identical to minus q. Okay, that is what happens because it wants to keep the boundary condition in a specific way. That's the only way that happens. What is the force between these? Because if I keep the charge here, definitely I see that the negative charge appears on the other side. They will attract each other, right? So there will be a force. And you can do the calculation, the force will be along z direction. And as an exercise, do that at home, the force will be equal the magnitude. I know the direction, of course, it's along z direction. The magnitude of force will be 1 divided by 4 pi epsilon naught q squared divided by z0 power of 2. And if you want the vectorial way, okay. In any cases, if you put a positive or negative charge, always it's attractive because the other charge appears with a negative sign. Okay. Fantastic. So essentially, that shows to us that always if you put a charge close to, let's say, a metal or close to an infinitely large, let's say, grounded conductive, then a dipole is appearing. Okay? And that's a problem that people, they face. Of course, I mean, I have to be very careful with this situation. That's a problem that people, they face when they want to bring current from one place to another place. Then you have to have a wire close to the earth, right? And when you have a wire close to the earth, there is the image of that, which always appears, of course, with the retardation. I don't want to talk about retardation. Tarek has taken the course with me on the retardation. It's very complicated situation. So you have to calculate how long does it take that charge will appear there. Okay, so physically, if you remember from the first lecture, assuming that I have this conductive here, right? I place the charge here. What we are talking about is electrostatic, which the charge is there, is not changing by time. But what happens if the charge is changing by time? So I will make the charge on and off. Then what is happening with the other charge there? That appears also on and off, but with a little bit of retardation. The retardation is regarded to the distance that requires that, let's say, the photons will interact with other side or create the other charge on the other side. And that appears with the speed of c. So if that happens, then there will be a small delay. And always what you ended up, it look like a dipole moment, which is dipole moment is oscillating a little bit with retardation in time. Okay, so it's getting very, very complicated, but that's true. It's boundary condition. You solve it and you will extend it to other problems that you may face. Fantastic. So beautiful. Can I give you another problem? Is there any question, by the way?
And can I ask a simple question? Why are we having a functionality of Z in our sigma, even though that has to be like in the surface? Is it like Z is equal to 0 all the time?
We have to, that is perfect question. Thank you very much. That should be at the surface of 0. Okay. I calculated sigma, but I did not say that should happen at the Z equal to 0. Thank you. Thank you, Nazain. Very good question. Because that is a charge distribution at Z equal to 0. I have to place it there. So essentially, there is a step missing here. So it will be epsilon naught, which goes away, by the way. It will be Q divided by 4 pi. And that will be minus Z. It will be twice with a negative charge. It will be minus 2Z0 divided by x squared plus y squared plus Z0 power of 2 power of 3 divided by 2. Is that right? Perfect. Wonderful. Okay. Guys, give me a second. I will be back, okay? So, fantastic. So that's the situation essentially that we are facing. Is there any question, any further questions or points that I missed? Okay, fantastic. So now let's go with something else, guys. Aha, now this time I will give you a charge, okay, at a distance of Z0, but the plate is not kept at at a potential 0. Now the potential of x, y, and z equal to 0 is equal to V0. First of all, which problem are we solving or we are facing? What is known at the surface?
phi itself, so it should be Dirichlet again.
Again, Dirichlet. So remember, you are dealing with GD of x and x prime. Okay. And that's a point charge here. Do we know the green function for these Dirichlet boundary condition? Are you sure? We just solved this problem. We solved it for potential equal to 0, but remember, green function was 0 at the surface. That is the only condition. Do you recall, right? So if you recall, phi of x for green, the Dirichlet boundary condition was this function, rho of x prime, d3 x prime gd of x and x prime d3 of x prime plus 1 divided by 4 pi, I think it was minus phi of x prime derivative in the direction of m prime of gd of x and x prime d2 of x prime. That's on the surface. Okay. Where do we have a permission to, when do we have a permission to use this relation? Whenever the potential on the surface is known, on the boundary condition is known. Do we know the potential on the boundary condition? Yes, it is it's V0. And what is the condition that we have for the green, for Dirichlet boundary condition? For the Dirichlet boundary condition, GD x and x prime at the boundary should be equal to 0. Not constant, should be equal to 0. Okay. Do you remember that we, for the similar problem, we found the GD. What was the GD? Was 1 divided by x squared plus y squared plus z minus z0 power of 2 power of 1/2 minus 1 divided by x squared plus y squared plus z z0 power of 2 power of 1/2 for z0 greater, so for z greater than 0. Do you agree? Good. What is g d x and x prime at the boundary? At the boundary means that z is equal to 0. So if you place it here, that will be equal to 0, which is what we found previously. Do you agree, guys, or do you have a problem? If there's any problem, let me know.
Just sorry, I think we're missing x prime on definition. Shouldn't be like x minus x or not?
No, I assume that the charge is in the plane.
Okay, sorry.
No worries. But in general, yes, it should be like that. We assume for this specific plane. Okay.
This might be a bit extreme, but shouldn't it be greater than or equal to 0 for z?
Yes, of course. That should be always greater and equal to 0. Because at the 0, we know that is equal to 0. That's a reason that always. Yeah, I agree with you. Also, if we do with the previous one, it does apply also. Okay, but does not apply to z negative, which is the point. As soon as we know the green function, and if you assume that the charge is also moving around, I mean, you can have a charge not at z equal to 0, but somewhere else, okay? Then the green function that we do have, that will be y minus y prime, and of course, x minus x prime, power of 2. So those parts, remember, I assume that only the charge is located at z0. That was the point that I want to raise. But here, essentially, if the charge has a volume, as you have a charge distribution, green function, the proper green function is x minus x prime power of 2 and plus y minus y prime power of 2 as well. Okay, like what we discussed previously. That should be replaced here. All right. So with the previous trick, we already found the problem. We already found the green function. Whenever we have the green function, then now we can resolve the problem. Even I can go further. I can say to you guys, is that clear, by the way? You can just simply replacing rho of x with q delta of x minus z0k, okay, and replacing inside of this expression, and you will get the potential, okay. You have to take the derivative of green function with respect to n prime, which is along the z direction. That's the only trick that you need. Is that clear? Do that as an exercise for yourself, just having a feeling about those expressions. Now let's go with a more complicated situation, which might sound a little bit difficult for you at the beginning, assuming that now the charge distribution here, x, y, and 0, is a specific function of x and y. For example, is a sine of x, cosine of y, right? Again, is a fixed boundary condition, which is, it's a well-known function at the boundary. Okay, for example, at this, that surface is periodic function, or may have a Gaussian distribution, is e power of minus x squared divided by w naught, or sigma, let's say in this way. For example, the charge distribution in the surface, which I'm watching it from here, the charge distribution is something like that. So it's a Gaussian distribution. So is e power of minus rho squared divided by rho 0 power of 2. Okay. So but it has a specific distribution for the charge. Can we solve this problem? Again, what is the problem? Is it Dirichlet or boundary? Sorry, Neumann boundary condition. Which one? Tarek?
It's Dirichlet.
Is it Dirichlet because we know the potential? Okay. Yeah. Fantastic. Here, even I don't have any charge distributions here. I don't have even charge distributions. That's the point. This is the problem that you already solved. You found the green function, g, d, x, and x prime, which is based on what, I mean, Edith and I, we discussed. It's 1 divided by x minus x prime minus 1 divided by x minus x second of x prime. Even there is no charge distribution, or if there is any charge distribution, it's up to you. And at the end, what I will have, again, I will have of 1 divided by 4 pi epsilon naught rho of x prime, g d of x and x prime, d 3 of x prime minus 1 divided by 4 pi integral of potential of x prime, which is on the boundary, which is on the surface, of derivative in the direction of n, which is normal to the surface, which is z, of green function of x and x prime, d2 of x prime. Okay, this is exactly the same problem. We already solved the problem. With charge distribution or without the charge distribution, this is the potential. As soon as you found the Green function, you have the freedom to do whatever you want with the charge distribution or without. So for example, in this explicit example that I just gave, I don't know what is the charge distribution. I don't care because the charge distribution here is 0. Then the potential will be given by -1 divided by 4 pi integral of the potential at the surface, which is, I will write it down explicitly, integral of dx prime integral of dy prime of phi of x prime and y prime and z equal to 0. And then derivative with respect to z prime of the Green function, which I gave it here, x and x prime. That's all. Okay. Here, remember, here we assumed that there is no charge distribution, but a specific potential at the boundary, which is this function. Essentially, you have to place phi 0 here. If you have a charge distribution, the first term also appears in the calculation. But remember, that's a general situation that you may face. With or without the charge distribution, that is the result for the potential as soon as you know the Green function. Without the charge distribution, simply you place the Green function, take the derivative in the direction of normal to the surface and placing there, and you will get the result. Good. So as an example, I will give you a charge distribution which is given by Gaussian, like what I have done here, and try to solve it and find out what is the potential in the other side. Okay. By the way, that can be done also in Physics 2, Fundamental of Physics course. It's just simple calculation. But now, even if you have a sphere here, which this sphere has specific charge distribution, then clearly you cannot solve these with the Physics 2 approach. You have to go with the Green function. You have to go with that language that we define here. Okay? Good. Questions? Fantastic. Let's go and solve another problem. Okay. From the plane, now we will go to, we have two options, cylinder or a sphere geometry. Let's go with a sphere because cylinder also is not difficult. It has some logarithmic approach that you have to be careful with it. Assuming that you have a sphere, which the radius of the sphere is A. These are three-dimensional objects, guys. Is a sphere, okay? And this sphere is kept at the potential of 0. So phi at the surface of sphere at let's write it properly. That is at 0 potential. If let's say, conductive sphere is kept at the potential of 0, then everywhere the potential will be 0. All right? If the potential is given 0, then it's 0. Assuming that now I am placing a charge at the front of it. Where? Here. I will place a charge of Q. What is happening? Physically, Nazan, you are muted.
Probably we'll have a charge distribution on the surface of the sphere.
Exactly. You will have a charge distribution. What is happening? It takes the charges from let's say, from the earth or the ground to keep the potential to be 0. And as a consequence, you have more charges on the surface, but specific arrangement. Positive, negative in some places, or positive or negative some places. You have to do the mathematics. Clear? The aim is finding potential here. Okay, in this region. Everywhere outside of the sphere, not inside. And that's the goal that we have. What is the problem? Dirichlet or Neumann? Tarek?
Would it still be Dirichlet?
Is it Dirichlet?
Hmm.
Is it Dirichlet? Problem is boundary problem. Oh, how should I solve it in MATLAB? Do you have any thoughts?
Well, again, we need to start finding the green function.
Yeah, I have to find the green function. How do I find the green function? I have to, the green function, since the potential is known at the boundary, the green function should be a function which will be 0 at the boundary, right? So it means that the GD of x and x prime should be equal to 0 at the boundary. Okay, where is the boundary? Is the surface of the sphere. So that green function at the surface of the sphere should be 0. Let's solve the problem in a different perspective. I put a charge here. So then the field, if you look at the field, then the field or potential will appear. So I have to do something else in order to get a specific potential there. Okay. And so let's do that this way. So if I have a charge of Q, you have a charge of minus Q prime. If Q prime is identical to the Q, that will be the field, right? That will be the field distribution. Okay. And that was the previous case that we find that the potential here is 0. All right. Which is normal to the surface. Now, assuming that one of the charge is weaker. So you have a Q, but the other one is minus Q prime. But when it's minus Q prime, then Q minus Q prime is a little bit, Q prime is smaller than Q. What happens? So the field here will go like this way. It will be less affected. it's look like a point charge, field here will be more affected. Right? Then you will see that the normal, when essentially the radius that you have, the normal, it will be shifted, let's say, towards the weaker charge. Okay, so we will do that, and the charge distribution, playing with the charge distribution, we will try to find out what is the other charge and where is the location of the other charge. So I will try to use this trick and find out what it should be the image charge in such a way that we can find out and find out the green function for this problem. So let's choose the coordinate for ourselves. So let's choose that. Maybe let me write it down again. So that's the problem that we have. So the surface is given by A, the distance of A. That is the place of the charge, which is located at Z. Let's call it from the center of this charge, the sphere. Let's call it Z0. And the charge is Q. And I don't know where is the location of image charge. And remember, that's also kept at the potential of 0. Okay, potential at the surface at R equal to A is equal to 0. And I don't know where is the place that the image charge appears, but definitely due to the symmetry should happen on these axes, right? That should happen on these axes. And it should be close to the charge. So it should happen somewhere here, which I will keep the distance as Z prime, maybe Z1, just to clarify. And what is the charge? I call it Q1. Okay. I don't know what is the value of Q1. I don't know also what is the distance of the charge, image charge there. The aim is finding the potential anywhere here outside of the sphere. Okay. What we are going to find? We are going to find the green function, which at the surface of the sphere is 0. That's the goal that we are going to do. And we are using the same approach that we did. We are placing a point charge there at the distance of Z0, and we are looking at the image charge that happens inside of the sphere or inside of the metal, such a way that the boundary condition is satisfied, and in such a way that the potential at the surface of the sphere is 0. So then the potential at any places is given by 1 divided by 4 pi epsilon naught. First, due to this charge, which is Q, and we are looking at any places here, which I call it X, okay, which is 1 divided by Q divided by 1 divided by X minus X0. X0 is the location or position of the real charge, Q, plus Q1, 1 divided by 4 pi epsilon naught, X minus X1, which X1 is the location of the image charge Q1. Good. So we can solve this in very complicated way, but let's go with simple approach. I assume that the vector is along this direction. I will call this n vector. A vector that is along this direction. It can be, for example, x, okay? But since I want to solve the problem in spherical coordinate, I will prefer to use the n as the direction which is pointing from the center and passing through the charge Q1 and Q, okay? That direction I will call it n, which is the vector that I have. And also I have another vector, which is r hat vector, which is normal to the surface of the sphere and is towards the point in the spherical coordinate. So this is look like the spherical coordinate r hat. All right, good. And of course we have theta hat, we have phi hat, but for our problem, I'm just assuming this specific case. So let's write the equation again. So phi at any places x is given by, well, let me write it with a different color. Phi at any place of x is equal to q divided by, let's write it in this way. 1 divided by 4 pi epsilon naught q divided by r hat, which is that x, by the way, guys, x is r hat in any direction that we are looking at it, minus z x0. X0 is, the vector is z0 in the direction of n hat. Do you agree? X0 is the location of the real charge, and location of real charge, which is means here, is x0 is equal to z0 in the direction of n hat.
Sorry, why do we only have r hat for the position of like phi x? Can't we have like we have to have the full?
What I have to
of
write,
course.
tell me.
So it has to be plus r sine theta hat, like. Oh, this is all enough for.
I'm asking you. Is that enough?
We should have theta hat and phi hat as well, right?
Really? Okay, let me write it down. It is an educational and pedagogical way. So you say that when I want to define x in the spherical coordinate, I have to write r hat, and you say theta hat as well, right? And phi hat.
This doesn't work properly because the dimensions are not.
Very clear. Of course it doesn't work. Of course does not work. You don't need to write it in this way. In the spherical coordinate, you write it r hat. Why? Because r hat is different for any location. R hat is a function of phi and is a function of theta as well, right?
Yeah.
It's not function of r, it's a function of phi and theta. Yeah. Clear?
Okay.
Any places r is changing, of course, is a magnitude, but the direction is function of phi or theta. Okay, you will write it in this way. Clear, guys? You got that? Fantastic. Beautiful. Now let's go with the other one, which is what plus Q1. Correct me if I do a mistake, guys. Okay, so and x again is r hat minus Z1 n hat. Is that correct? That's the potential due to the point charges we do have at location of Z0, Z1 with the charge of Q and Q1 in the spherical coordinate. Don't be shy. If you have questions, just ask, because it's good. We will have discussion. Good. Let's go with the next step. What is with the potential? What we know about the potential? Potential at the surface of the sphere should be equal to 0. Exactly. What is the surface of the sphere? Is R or AR hat. Any places on the sphere should be 0. Doesn't matter which location you are watching. As soon as the distance is kept at A, the potential should be equal to 0. So then phi at x, which is AR hat, is equal to 0. And therefore, that means that 1 divided by 4 pi epsilon 0 Q divided by AR hat minus Z0 n hat plus Q1 divided by AR hat minus Z0 n hat should be equal to 0. Good.
That be Z1 for the second thing.
Yes, thank you very much. Exactly. That should be Z1. Beautiful. Any questions so far? Nope. Now I have to do a trick. I have to do a trick. If n hat is along the different direction, let's call it I hat. So that will be I hat. Then I can do something else. I can explicitly expand these and can find that, which you will see in a second. I want to find a trick that you can just by dividing the both part with something else, you can get the result. And I'm not able to to do that. Z1, let's take the Z1 out. That would take the Z0 out. That doesn't help as well. Okay, let's do that then. I will go with the brute force calculation and see what is happening. So then remember, that's the direction of n hat. Okay, oh, sorry. That's the direction of n hat, which we do have. And that's the direction of r hat. So essentially, I have two vectors of n and a vector of r hat. All right, which one is the position of the charge, and the other one is any places in a space that is rotating. Okay. So assuming that the angle between these two is alpha, is two vectors, and they can be in a plane. The angle between these two is alpha, and alpha is changing from 0 to, let's say, 180 degrees in any way that you want. You can also write it in a phi and theta coordinate, but I don't want to go with this complicated situation. Let's write it in this way. How do you find this relationship? So you will go with 1 divided by 4 pi epsilon 0, and that is Q divided by the difference, but magnitude of difference of two vectors of AR hat minus Z0 n hat. That will be square root of the first term, which is a square, the first vector, absolute value. I'm using this relation, by the way. If you have two vectors of A and B, two vector of A and B, and the angle is alpha, then what is A minus B? A minus B is A squared plus B squared minus 2AB cosine of the angle between these two, alpha power of 1/2. Okay, and I'm going with this relation. Let's place it here. So it will be A squared plus Z0 power of 2 minus 2AZ0. The angle between these two is a cosine of alpha. And for the second term will be plus Q1 divided by square root of A squared plus Z0, Z1 power of 2 minus 2AZ1 cosine of alpha. Okay, and that should be equal to 0. So I will take away A squared. I'll factor out A squared here. I will factor out Z1 squared here. Let's do that. Then that will be, I don't take care of 1 divided by 4 pi epsilon naught because the other side is 0. So that will be Q divided by A square root of 1 plus Z0 divided by A power of 2 minus 2Z0 divided by A cosine of alpha. And the other side, as I say, I'm taking away, what time is it? Oh, sorry guys, it will be done in 3 minutes. Not, if we cannot do that, then we will follow up with the next lecture. Q1 divided by Z1 square root of 1 plus A divided by Z1. Note that I just swap. So I go first with the Z1 minus 2A divided by Z1 cosine of alpha. Okay, equal to 0. Then Q divided by square root of 1 plus Z0 divided by A power of 2 minus 2Z0 divided by A cosine of alpha plus Q1 A divided by Z1. I multiply both sides by A, and I took away the Z1 in the denominator, and I will place it. I just place it in the Q1. Okay, and that will be 1 plus A divided by Z1 power of 2 minus 2A divided by Z1 cosine of alpha equal to 0. Okay. I will do this trick. This can be equal to 0 as soon as Q is equal to minus A divided by Z1 Q1, and at the same time Z0 divided by A is equal to A divided by Z1. Do you agree? So here, then I find out that the Q1 is equal to minus Z1 divided by AQ, and Z1 is equal to A squared divided by Z0. Agreed? I will conclude it and in 1 minute, and then